Then response of the first order systems to unit step input. This is very important one, so listen carefully. R of t equal to U of t, R of s equal to 1 of s, because I am going to apply a unit step input. And G of s already we know in the previous page where I introduced about the first order system, which is equal to 1 by 1 plus tau s. And now for R of s, I will be applying 1 by s, right? Because I am going to find, I am interested to find what is the response of the first order system if I am going to apply a unit step input. Unit step input is nothing but your standard test signal, right? So therefore, because just like that, using mathematical derivations, mathematical equations, we can able to solve the equations, and we can find the values, and you can get marks also. That doesn't matter. But what is the importance, or how it is related with your transducers, or how it is related with the measuring instrument is very important here. Okay, because before applying any input signal to the any system, we don't know the input signal which is going to be applied. Okay, so therefore we have to apply the test signals, because we don't know any measuring instrument or any transducer is what, and what kind of input signal is going to be given, that we don't. So we have to use this test signal. Okay, right? But then G of s equal to 1 by 1 plus tau s, and C of s equal to G of s into R of s, where C of s is output, G of s is transfer function, R of s is input, and therefore C of s equal to 1 by s into 1 by 1 plus tau s. And left side 1 by s into 1 plus tau s, which is equal to a by, it is partial fraction, a by s plus b by 1 plus tau s. And we'll take the, we will what is it, we will take the cross multiplication, and you can find what is in this side. We are not going to consider. Okay, for in order to find a, I have to consider only these two, and for b I have to consider only these, right? So a equal to cross multiplying s divided by s into 1 plus tau is, this s and s get cancelled, and at s equal to 0 is good. This is going to be the procedure, right? You might be knowing, because already you people have completed this. At s equal to 0, therefore numerator 1, and this tau into s, that becomes 0, 1 plus 1, 0 becomes 1, denominator is 1 and numerator is 1, therefore equal to 1, 1 by 1, which is nothing but 1. Okay. And similarly, we have to find the b value. So similarly, cross multiplying it, will be getting b equal to 1 plus tau s divided by s into 1 plus tau s. 1 plus tau s and 1 plus tau s gets cancelled. Add s equal to minus 1 by tau, that is also explained here. That is 1 plus tau is equal to 0. Tau is equal to minus 1, s equal to minus 1 by tau. So this is the value you have to supply for yes. So therefore, b equal to 1 by minus 1 by tau, that becomes b equal to minus tau. Therefore, C of s equal to 1 by s minus tau by 1 plus tau s, and taking inverse Laplace transform, this becomes C of t equal to 1 minus e power minus t by tau. Okay, now we'll be just we are going to discuss what is the response of the first order systems to the step input, that is shown here. And previously also we got the same value, because that is an RC, which is the first RC circuit, which is the first order system. This is for the general. Okay, if it is not specified, then we have to, you can refer with the second one. Okay, general system. Then response of the first order system, which is already I explained, and this is going to be input, and this is going to be the output, and this is the error. Okay, and within the time tau, the output is going to reach 0.632 times of input. Okay, so this is an important calculation. You have to remember that one. Then time constant tau is given as the time to reach 63.2% of its final value. Okay, then the second diagram, which is shown here, the second one, that is nothing but an error. Okay, error em of t, which is equal to r of t minus c of t. So 1 r of t is nothing but 1, that we know, and c of t just now we derived and we found it. So the same value that I am using here, 1 minus, within bracket, this is nothing but our c of t. Okay, taking this bracket, this one and this one gets cancelled, and minus of minus this become plus. So therefore this becomes e power minus t by tau. So the error equal to e power minus t by tau. This is variation of dynamic error, the variation of dynamic error is shown in figure, and steady state error, ESS, this is again a formula, right? ESS, steady state error, is given as limit t tends to infinity, em of t, which is equal to, okay, at time t tends to infinity. In this equation, we have to substitute what happens if t tends to infinity. Okay, e power minus infinity is nothing but a decaying one. That is the basic fundamental formula for maths. Okay, if it is if an exponential is going to have a positive sign, it is going to increase. Then if it is going to have a negative, then that's going to decay. That too, if time becomes infinite, definitely it's going to reach zero. Therefore, using that convention, I'm going to substitute my steady state error equal to 0. So this is an important conclusion. First order system tracks the unit step input with zero static error. Okay, and this one is a graph is shown here between time t and output c of t, and this is input r of t, which is equal to t, and this is output c of t equal to t minus tau into 1 minus e power minus t by tau, and this gap is nothing but steady state error. And dynamic error, similarly, how we calculated for the step input, similarly we have to calculate for the ramp input, em of t equal to r of t minus t of t, and which is equal to tau into 1 minus e power minus t by tau. Then steady state error is where this is the ESS, which is equal to em of t, that is dynamic error, where time t tends to infinity. Therefore, we will be getting this entire equation, this becomes 0, this e power minus t by tau becomes 0, because already we know that. Then 1 minus 0 is nothing but 1, so 1 into tau will be getting tau here. Okay, if input is et, then ESS is e tau. Okay, this is the important finding. Then we are going to discuss about the impulse response of the first order system. When input is r of t, which is equal to a del of t, and this is also a universal question, so please make a note. R of t equal to a del of t, and r of s is equal to a, and c of s equal to g of s into r of s, which is equal to a by 1 plus tau s, and taking, because there is no need for a partial fraction at all. This is very simple, so directly we can find the inverse Laplace transform. Therefore, investigating the inverse Laplace transform, c of t equal to a by tau into e power minus t by tau, and these two diagrams are shown the impulse function, but this time t is going to be much smaller. Okay, then the impulse response of the first order system is going to be a decaying one. Okay. Then we move to the second order system. We started with transfer function, then zeroth order, then first order electrical circuit, then excited circuit, then response unit step response, then unit ramp response, then unit impulse response, then we move to the response of the second order system. So second order system, the differential equation is going to be which is given as, will be having in left hand side will be having a2, a1, a0, and right hand side will be having just b0. And typical second order system is going to be a mass damper system, and mechanical, which is a mechanical system, and will be having m x double dot of t, which is nothing but m d square x of t by dt square. Okay, x double dot is nothing but d square differential, that is second order differential. Okay. Then if one simple dot is going to be there, then that is nothing but dp dt. Two dots are like d square by dt square, right? And so mass is m, and then damper is b, and k is going to be a spring. Okay, this is the typical second order system. So m into x double dot of c of t plus b x of t plus k x of t, which is equal to f of t. And taking the Laplace transform for the equation will be getting m square x of s plus bs x of s plus k x of s, which is equal to f of s. Then transfer function is nothing but output divided by input. Here the input is going to be the force f. F is nothing but force. Okay, x of s by f of s, which is equal to 1 by ms square plus bs plus k, and g of s equal to k into x of s by f of s, just a dimensionless transfer function. Okay, So k by ms square plus bs plus k. Okay, now we having we're going to divide the equation by m. Therefore, denominator k by m and denominator s square plus b by m of s plus k by m. Then we having k by m into this is just a small manipulation. That manipulation also I have explained here. The manipulation also I have explained here. Okay, which is given as b by 2 root of km into k by m. K, this k and this k is going to get cancelled, and this is root m and this is root m. This root m in the denominator, and this is also square root of 1 by m. This is nothing but 2m. Okay, that is only given here. And the 2 here and here we have included, multiplied and divided 2. Okay, it is not going to change the previous equation. Am I making it clear? Okay, this one and this one, both the equations are same. Just for manipulation, we have introduced some changes. And the last spring factor is going to be k by m. The transfer function equal to is given as omega n square by s square into 2 zeta omega n s plus omega n square, where omega n is the natural frequency and square root of k by m is called as the natural frequency and radians per second, and zeta is the damping ratio, which is given as b by 2 square root of k m. And the equation 1 is the second order transfer function, and for the second order transfer function we'll be analyzing the second order transfer function for 3 different cases, but for transducer I'm going to use only the underdamped system. We should know what is damping. The damping is nothing but zeta. If the zeta value is greater than 1, that system is called as over damping. The diagram is shown with that. Okay, the distance between the gap between the output and the input is going to be more if it is the over damped system, and critically damped, the distance is going to be small. Where zeta equal to 1, for underdamped zeta is less than 1, which is going to have some oscillations. Okay. Minus 2 zeta omega n, because the left hand side is 0, c equal to minus 2 zeta omega n, and substituting and finding the equation. And the equation is going to be 1 by s minus s plus 2 zeta omega n square plus 2 zeta omega n s plus omega n square. Then we are going to do some manipulation, adding and subtracting zeta square omega n square to the denominator in the second term. Then do some manipulations. The manipulations you can easily understand. This is going to be s square plus 2 zeta omega n square. We'll be adding and subtracting this, and this zeta square omega n square is going to be added here, and this omega n square minus zeta square omega n square is separated, and this is going to give a plus b whole square. Then s plus zeta omega n the whole square is going to be a plus b, and here omega n I'm going to take it as a common, and then be getting 1 minus zeta square. Omega n square into 1 minus zeta square is considered as omega d square, and omega d equal to omega n into square root of 1 minus zeta square. So this is going to be divided by s plus omega n omega n square plus omega d square. Okay, and then now we are going to divide the two terms. Okay, 1 by s minus s plus 2 zeta omega n is going to be divided into zeta omega n and zeta omega n, right? So that is given here. 1 by s is going to be the first term, then second term is going to be s plus zeta omega n divided by s plus zeta omega n the whole square plus omega d square minus zeta omega n divided by s plus zeta omega n the whole square plus omega d square. This is going to be, suppose for example in the numerator we are having 3a. Okay, in the denominator we are going to have some s plus b. Okay, so that can be written as the 3a, or 2a of the numerator can be written as a divided by s plus b plus a divided by s plus b. So numerator, this kind of, because denominator is same, so I'm just dividing it. Okay, I hope you can. It is a very simple mathematical manipulations, right? Then after dividing, we'll be doing multiplying and dividing by omega t in the third term of the equation. So c of s of equal to 1 by s minus s plus 0 omega n divided by s plus 0 omega n square plus omega d square, because second term, first term we have not touched. Then the third term we are going to multiply and divide by omega d. So therefore I am going to have 0 omega n divided by omega d into omega d by s plus 0 omega n square plus omega d square. Now this is why we are doing all this manipulation, is in order to make use of the formulas of Laplace, inverse Laplace transform. Nothing more than that. Therefore now we are having three equations. The first one is 1 by s, the second one is minus z plus s plus 0 omega n divided by s plus 0 omega n square plus omega d square. Then the third is minus 0 omega n by omega d into omega d by s plus 0 omega n square plus omega d square. Therefore, taking inverse Laplace transform, 0 of t equal to 1 minus e power minus 0 omega n g into cos omega dt minus 0 omega n by omega d e power minus 0 omega n t into sin omega dt. 1 minus e power minus 0 omega n t is going to be common in both the cases, both the second and third terms. So I am taking it common. And cos omega dt plus 0 omega n, omega d, we already know that omega d is nothing but omega n into square root of 1 minus zeta square. I am substituting, and in the third term omega n gets cancelled, sin omega dt by square root of 1 minus zeta square. So I am writing 1 minus e power minus 0 omega n t, bracket open, cos omega dt plus theta by 1 square root of 1 minus zeta square into sin omega dt. That's simple manipulations. Here we'll be having 1 minus e power minus 0 omega n t by 1 square root of 1 minus zeta square into 1 minus square root of 1 minus zeta square cos omega dt plus theta sin omega dt. For that is we have taken 1 minus zeta square as a common, and that's why we introduce, or we multiplied to the taking square root of 1 minus zeta square as a common, right? That is done here. Then in the second equation of this slide, just we have interchanged the sin term and cos term, right? Here triangle is introduced here. Theta is going to be the adjacent side, and square root of 1 minus zeta square is the opposite side, and hypotenuse is 1. So sin theta, cos theta, tan theta is defined here. So we will be using this equations in the previous equation. So what is our previous equation? Our equation is going to be that is in the 1 minus e power, that is before the bracket we are not going to introduce any changes. Instead, within the bracket only we will be introducing the changes, or we are going to apply the triangle, right? I am making it clear. So before the bracket, what is the term we are having? 1 minus e power minus 0 omega n t by square root of 1 minus zeta square. We are not going to disturb, and within the bracket the zeta is going to be replaced by means of cos theta, right? This is replaced by cos theta, that is shown here. Then the second term, right, 1 minus zeta square is going to be replaced by sin theta. Okay, so finally we will be getting, this is nothing but your sin A cos B plus cos A sin B. So I can able to write, or I can able to simplify sin of A plus B. So other things remain same. The theta is equal to tan inverse 1 of square root of 1 minus zeta square by theta, and this is going to be the underdamped system, second order systems, second order transfer function with the underdamping, and then the response of your unit step input. Okay, thank you.